All right, we'll cover a few more topics in probability, and just like in the previous lesson when we used trees and lattices, today we'll use Venn diagrams. So whenever we can represent it graphically, it helps prevent errors, or it can help prevent errors. And today we'll also talk about unions and intersections. So we talked about sample space in the previous lesson. Sample space is all the possible outcomes, and an event is a subset of the sample space. An event is some part of that. In the Venn diagram, the sample space is the area in the rectangle, and events are these regions of the sample space. So we could say that the sample space is all of this area, and then we have event A and event B. We'll just represent this area. The total area of the rectangle is 1. To help us calculate probabilities, let's just talk about point 1 being the area outside of the events. And then we could say point 2, these are just examples. Point 2 is the area there. And then we have this area, point 3, and this area is point 4. And now we can talk about probabilities. The probability of event A is 0.5 because A has a total area of 0.5, including that, and that's called the intersection. The probability of event B is 0.6 because it's the total area. And the probability of something in the sample space is 1 because the total area is 1, and we could add up 0.1 plus 0.4 plus 0.2 plus 0.3. They all have to add up to 1. Emphasize that it is not a decimal like these. It's not less than 1. The intersection is, the notation is this, and here's an N or an upside down U. There's no line on it though. We don't write it like this. We just write it like that for intersection. So the probability of the intersection is 0.2. The intersection is the region common to both events. Union. The notation for union is with a U shape, and when we look at the Venn diagram, the union is the area of A and B together. So it would be 0.3 plus 0.2 plus 0.4, 0.9. But we also have a formula for the union, and that is the probability of the two events, the sum of their probabilities, minus one intersection. And so I emphasized that we're subtracting one intersection because when we add all of A, we've added this once, the intersection. The intersection is part of A. And then when we add all of B, we're adding the intersection twice. We're adding the intersection again. So this is just saying by looking at A, we include the intersection already, and this includes the intersection again. So let's subtract the intersection. And that's why we have to subtract that. So all of A is 0.5, all of B is 0.6, minus the intersection, and we get 0.9. So we can count the, we can just add up the area in the Venn diagram, or we can also use a formula. The complement is everything other than what's specified. So this mark means the complement of A, means everything outside of A. One way to do that is we'll take 1 minus A, and that'll give us the complement of A. The probability of the complement of B, 1 minus the probability of B, 1 minus 0.6, and we get 0.4. And here we're using the complement of A, and I'm doing the probability of the complement. This just says the complement. So the complement and the probability are not the same thing. I really should have said probability of the complement of A is P of A prime. And with these, rather than trying to decide how to use a formula, and maybe some of these we don't even have a formula, we can just use a Venn diagram for all of these. So let's just draw a Venn diagram based on this. This is all of A is 0.3. Here's the intersection is 0.1. That means this region must be 0.2 so that all of A is 0.3. And this region must be 0.1 because B is 0.2. So 0.1 plus 0.1 gives us 0.2. Then the complement of the union of A and B, or this region out here, is 0.6 because all of this is 0.4. So the probability of A union B, call that S for sample space, A union B. If we just look at the Venn diagram, it'll be helpful to visualize it like this. A union B means everything in A and everything in B, and or everything in B. So that means just add up that region, that area. 0.2 plus 0.1 plus 0.1 is 0.4. Remember that we can also do this with probability of A plus probability of B minus probability of A intersect B, and we'll get A is 0.3, B is 0.2, intersection is 0.1. This adds up to 0.4. A intersect the complement of B. So let's visualize that. So we want everything that's in A and not in B. So if we shaded all of, it's better just to say, just do it all at once. In A and not in B. So let's just check. Is this point in A and is it not in B? Yes. Is this point in A? Yes. But it is in B. It's not in the complement of B. Is this point in A? No. So we're looking for that region. And we can just look up the diagram and say that it's 0.2. All right. And part C, probability of the complement of A. complement of A, everything outside of A, so we're going to shade everything outside of A, and then just add up that area. So we don't want any of this. We could say it's 0.6 plus 0.1 is 0.7. We can also say that it is 1. The whole rectangle is 1 minus 0.3. Either way, we'll get 0.7. The complement of the union of A and B. So here's the union of A and B, and we want the complement of that. So it's everything outside of A and B. And we can just count up that area here. It's 0.6, or it's 1 minus 0.4. Probability of A intersect. Oh, we did that one twice. We don't have to do E. We already did that one. All right, pause the video and try this one. Let's draw the Venn diagram. All of A is 0.3 and all of B is 0.5, but altogether it's 0.6. So we can't say 0.3 and 0.5 because that would add up to 0.8. So we have to decide how much is in here. And we could use the formula. We could also just guess and say, well, if I put 0.1 there, this is a 0.2 and that's a 0.4, and then check. Is this going to add up to 6? No. Let's try. Right now it adds up to 0.7, so let's do one more. It's 0.2. That would make this 0.1, and this would be 0.3. And now the union is 0.6. So we have 0.1, 0.2, and 0.3. We could also use the formula minus intersection. So we have the union is given 0.6, probability of A, probability of B, minus the intersection that we can solve for. So we have 0.8, subtract it, and we get negative 0.2, and we can see the intersection. Divide by negative, and we see the intersection is 0.2. Or we can just guess and check in the diagram. The union is 0.6, so we know that the complement of the union is 0.4. And here we'll have B intersect complement of A. So it's in B and not in A. So this point is not in B, so we don't use it. It has to be in B. This point is in B, so let's check it. Is it also not in A? It has to not be in A, but this is in A, so we don't use that one. This is in B, and it's not in A, so we want that. And this point is not in B, so we can't use it. And we're going to find that region. We just look up here and it's 0.3. We need the intersection, and that's right here. For this problem, we could have done all of this work. We've already done it, so we can just look at that and see that it's 0.2. And we need everything outside of the intersection of A and B. All right. So we want to find the intersection and then shade everything outside of the intersection. Here's the intersection, and we want everything outside of the intersection. We know the intersection is 0.2, so that means everything else must be 0.8 because it all has to add up to 1. We could also just say it's 1 minus 0.2, and we get 0.8. So, in part A, let's say event A, just to use some notation, we have event A is selecting an M. And we know that event S is selecting any letter. So now we talk about the number in the sample space is 11. The number in event A is 2 because we have 2 M's. That increases the possibility of getting an M. And we also have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So that's all possible choices, and we'll have the probability of A is the number in A divided by the number in the sample space. So that's 2 out of 11. Event B is a consonant. Consonant is not a vowel. So we have the number in the sample space is 11. The number in event B. We have to, event B is a consonant, so let's look up all the consonants. 1, 2, 3, 4, 5, 6, 7. So we don't include I, A, E, and we have 7 consonants. So the probability of choosing a consonant is 7 over 11. we could do this as saying event C is not an I, or we can say event C is an I, and then we'll find the complement of C. And we could have done that here also. We said B was a vowel, then we would just say the complement of B. So here, if event C is selecting an I, then we want the probability of not selecting an I, and that's going to be 1 minus the probability of selecting an I. Event C is selecting an I, so let's look at that. There's one I, so that's 1 out of 11. So 1 minus 1 out of 11 is 10 over 11. There's the probability of not selecting an I. All right, try this one. It's a little different than the previous problem, so make sure you identify the events and the sample space, and then just count up the possibilities in each of those. We're also talking about it can be a consonant or a letter from the word Jordan, and so it can be in either one or in both. Pause the video and try this one. So the sample space is all the letters in the alphabet, A, B, C. The number in the sample space is 26. Let's say event A is selecting a consonant. So we have a consonant, the event of selecting a consonant, or a letter from this word, Jordan. So event B will be all right, so consonant, all the non-vowels, and we won't count Y as a vowel. Y will be a consonant. So let's look at the number of consonants. We have A, E, I, O, U, so we have 5 vowels. We have 21 consonants. The number in B, how many letters are in Jordan? We have 6, and there are 6 different letters. That's important. So now we want to look at the probability of the letter that we choose from the alphabet. What's the probability that it's from that it is a consonant or a letter from Jordan? So we have the probability of A union B. So when it says or, we know it's talking about a union. It could be in either one or in both. We have the formula, the probability of A plus the probability of B minus the probability of their intersection. And the probability of a consonant is 21 over 26. The probability of a letter being from Jordan is 6 over 26. And the probability of their intersection is just going to be all the consonants in Jordan. So we have 1, 2, 3, 4 consonants in Jordan. So that's the intersection of consonants and Jordan. 4 out of 26. And we get 23 over 26. We can also make a Venn diagram. We're selecting something out of the alphabet, the sample space. And when we're starting a Venn diagram, let's go ahead and put the total here, and then we can figure out how to break up the numbers. And so event A is a consonant, event B is Jordan, and let's start looking at the intersection of consonants and Jordan. Well, we have J, R, D, N. Those are consonants and in Jordan. And then we have all the vowels. This would be all the consonants in the alphabet, and these would be the other letters of Jordan. So we have Jordan, we have O and A. So these are letters that are in Jordan, and they're not consonants. We have a lot of letters in here. So now let's look at the numbers. And we look at the number in each region. We know there's 4 in the intersection. There are 2 here. And then consonants, we have 21 consonants, so we'll have 17 consonants that are not in Jordan. And if we add all this up, we have 6, that's 23, and that'll give us 3 left in the alphabet that are not a consonant and not in Jordan. Those are the 3 vowels that are in neither of these events. So if we did it this way, and we want the union, we can just add this up. 6 plus 17 is 23. So that works out. We could have done it with a Venn diagram, or we can do it with the formula. So when you do a Venn diagram, this is kind of like the rough draft, where we start thinking of how all the letters and the letters are placed, and then we can identify how many are in each region. Okay, and we'll stop there.